Measurements provide the information that is the basis of most of the hypotheses, theories, and laws in chemistry. So every measurement needs two important parts. It needs a number and it needs a unit. So when you're trying to weigh something, for example, you can't say that it weighs 18, because if you just give a number without giving a unit, then that number is meaningless. We don't know what to compare that to. We don't know what it's relative to. So if I want to weigh something and I say that it weighs 18 grams or 18 kilograms or 18 pounds, the number itself is very important, but equally important is the unit, grams or kilograms or pounds. So whenever we're taking a measurement, we always need both parts. We need the value, the magnitude, and we also need the unit. So in chemistry, we use an updated version of the metric system known as the International System of Units, or SI units. So if you grew up here in the United States, then you're familiar with inches and pounds, and fortunately or unfortunately, I suppose at least you won't be familiar with it, whether or not it's a good thing or a bad thing. The sciences generally use the metric system rather than the imperial system. So it's something that if you're not familiar with, it's really important to learn how this system works. So the SI base units for length is a meter, mass is a kilogram, time is a second, temperature is Kelvin, electric current is the ampere, amount of substance is a mole, and the luminous intensity is the candela. We will talk in a later term, in winter or spring, we'll talk a bit about electric current. We talk a lot about length and mass and time and temperature and the amount of substance. We will never really talk about luminous intensity, in this course anyway. So units can, a kilogram, for example, is a unit that's fairly large. And if we're trying to talk about the mass of something that's really, really small, talking about the mass of a single atom in kilograms might be a silly choice because it's a really big unit. Or if we were talking about a ton, for example, if I'm trying to talk about how much an atom weighs and I'm using tons, that's probably the wrong unit, because a ton is a unit that would be used to describe the mass of something that's really large, that weighs a lot. So to make these units bigger or smaller, we can stick with a meter. A meter is about 3 feet, right? Well, I can add these prefixes in front of meter to change how big the meter is. So if I have a centimeter, then there's 100 centimeters in a meter. Or I could have a millimeter, which there are 1,000 millimeters in a meter, or a micrometer, or a nanometer, or a picometer, or a femtometer. So adding these prefixes in front of the base unit changes how big that unit is. So millimeters are smaller than meters. Millimeters are smaller than centimeters. And we can add these same prefixes in front of any of these units. So kilo is actually already a prefix. So the base unit here is gram, and I can have a gram or a centigram or a milligram or a microgram or a nanogram. I can have a second or a millisecond or a microsecond or a nanosecond. I can have a Kelvin or a millikelvin or a microkelvin. So all of these prefixes, they're interchangeable. They can fit in front of any of those units. And whenever they go in front of a unit, they always apply this factor to make it smaller. In this case, all of these prefixes are making them smaller. There's another set of prefixes that makes units get bigger. So kilo in kilogram. That means a kilo is 1,000. It's a factor of 10 to the third, which is 1,000. So if I have a kilogram, that's 1,000 grams. A mega Mega prefix is 10 to the 6th, a million. So a megagram is a million grams. Giga is 10 to the 9th. Tera is 10 to the 12th. So when we are in chemistry, when we're talking about the measurements and the values that we're going to encounter most often in chemistry, they're usually small values. So we'll see kilo sometimes, but we won't often see mega or giga or tera. We don't use those prefixes in chemistry because in chemistry we're usually talking about molecules and atoms and very small quantities of substances, maybe a gram or even less. So when we're talking about these really small substances, generally these prefixes are more appropriate, and these are the ones that we encounter more often. We talk about milli and micro and nano quite a lot, and sometimes centi gets in there too. So these 10 to the minus third milli, 10 to the minus 6 micro, 10 to the minus 9 nano, those are important factors that we'll encounter pretty often. What I will say about this table here is it's important to know that centi has the symbol little c and that it applies the factor of 10 to the minus 2. So committing most of this table to memory is going to be a really important part moving forward. It's going to help a lot if you know what these values are without having to look them up in the table every single time. So femto and pico, we won't encounter those very often, but like I said, milli, micro, nano, centi, to some extent, these four are generally pretty important. And I would also just draw your attention here to the symbol for micro. It's kind of a U, right? If I put my pointer here, you can see that it looks kind of like a U, but then it's got this extra little tail in front. So this symbol is called a mu. So the mu is the symbol for micro, since the little m is already the symbol for milli. So whenever you see this, sometimes it's just a U, sometimes it'll be replaced with just a U. Whenever you see that symbol, that designates the prefix micro, 10 to the minus 6. Okay, so length, the SI unit length is the meter, and where did these units come from? What are they based on? Well, maybe you know the story of where they came from for the imperial measurements. We have a measurement of a foot. Well, the story goes that that was actually the length of some king's foot. And so the king's foot was about 12 inches. And so there was this, a unit of measurement developed that was called a foot. So units are always based on something. They're always relative to something, so that when I want to check if my measurement's correct, I can go and see what it is that my unit means. What is it measured relative to? So in the case of the meter, it was intended to be 1/10,000,000th of the distance from the North Pole to the equator. So that, in practice, is also pretty hard to measure, since the distance from the North Pole to the equator is pretty gigantic. So now, the way that they designate, that they define what a meter is to say that a meter is defined as the distance light travels in a vacuum in 1/299,792,558th of 1 second. So, you know, the speed of light is constant. Light always goes the same speed in a vacuum anyhow. So in a vacuum, if we measure the distance that light travels in this amount of time, which as you can see is an incredibly small amount of time, but the distance that light would travel in that amount of time is 1 meter, exactly 1 meter. Here's some relative lengths. So a meter is a little bit bigger than a yard. You know, a football field is 100 yards. So 100 meters would be a little bit bigger than that. A centimeter, there's 100 centimeters in a meter. So centimeters are much smaller than meters. An inch is about 2.5 centimeters. So inches and centimeters are pretty equivalent. You can think that an inch and centimeters are about the same thing. Meters and yards are about the same thing. The unit of mass, the SI unit of mass is the kilogram. And like we were saying before, kilo is a prefix, which means 1,000. So kilogram means 1,000 grams. So the kilogram is the base unit rather than the gram because of this whole size issue we were talking about a minute ago. That when things are large, it makes sense to use kilograms, and when we're trying to measure things that are small, it makes sense to use smaller units. Well, most of the things that were being measured when this was decided were being measured in the range of kilograms. So kilogram was was chosen as the unit, and also kilogram is a component of a lot of other SI units, like the unit of force, for example, uses kilogram as the unit of mass when we're doing those derivations. So there's a couple of reasons why kilogram is the unit rather than gram. So there is actually, what is a kilogram based on? Well, there's actually a device, a item called the kilogram, and the kilogram is a metal slug, kind of like a cylinder, that was made of a very specific alloy that was resistant to oxidation, so it wouldn't gain any oxygen particles and it wouldn't lose anything to corrosion. This special alloy, and this metal slug here that you see housed inside these glass containers, this thing weighs exactly 1.0000000 kilograms. So this item was the kilogram that everybody based their measurements on. And this kilogram was sent around the world to different countries, so different countries could calibrate their measurement equipment using the kilogram, so that when scientists were taking measurements in different labs in different countries in the world, they would be measuring the same quantities because their devices would all be calibrated to this same item, this kilogram right here. The SI unit of temperature is the Kelvin. So we say degrees Celsius or degrees Fahrenheit, but there is no degree Kelvin. So it's 200 degrees Celsius, or it's 200 degrees Fahrenheit, or it's 200 Kelvin. So there are no degrees Kelvin, it's just Kelvin. So the size of a Celsius degree and the size of a Kelvin degree, so the size of a Celsius degree and the size of a Kelvin are the same. So between water freezes at 0 Celsius and boils at 100 Celsius, water freezes at 273.15 Kelvin and it boils at 373.15 Kelvin. So there's 100 Kelvin between freezing water and boiling water. There's 100 degrees Celsius between freezing water and boiling water. So the size of a degree Celsius and the size of a Kelvin are the same, but they're not the same as the size of a degree Fahrenheit, because water freezes at 32 degrees Fahrenheit and boils at 212. So there are 180 degrees Fahrenheit between freezing and boiling water, whereas there's only 100 degrees Celsius and 100 Kelvin. So that means that these Fahrenheit degrees are smaller. Right? I can fit almost twice as many of them in this same space. So a Fahrenheit degree is in fact 5/9 of the size of a degree Celsius. So the size of a degree Celsius and Kelvin are the same. The only difference is where 0 is. 0 for Celsius is freezing water. 0 for Kelvin is absolute 0, the coldest temperature in the universe. There's no such thing as a negative Kelvin temperature because 0 is as low as it goes. It can't get lower than 0 Kelvin. It can get lower than 0 degrees Celsius, obviously, because 0 is just an arbitrary place where we set the scale to correspond to the freezing point of water. And degrees Fahrenheit, it has a different freezing point, a different boiling point, and the size of the degrees are different. So Fahrenheit is far different than Celsius and Kelvin. Celsius and Kelvin scales are fairly similar to each other. Okay, finally, the SI unit of time is the second. Now, obviously, seconds are the same in the imperial system and the metric system, so we don't need to talk about any differences between seconds and minutes and hours. Okay, so there are these standard units, and then there are what we call derived units, so that we can talk about certain properties using combinations of these units. So volume is the measure of the amount of space occupied by an object, and so we can generally describe volume using a cubic meter, which is a meter times a meter times a meter, so length, width, and height. And we can also talk about volume using other units like these down here, a cubic decimeter or a cubic centimeter. Here are some relative values of these different volume measurements. Here's a cubic meter. Here is a cubic decimeter. And then this little tiny piece here would be a cubic centimeter. So a cubic centimeter is about the width of a dime. And finally, density is the amount of substance there is per unit volume. So it's a ratio of mass to volume. So if there are a lot of atoms in a small space, then we might say that that substance has a high density. And if there's not a lot of atoms, there's maybe a lot of open space or not a lot of mass in a small volume, then we might say that that material has a low density. So the units that are generally used for density are grams per cubic centimeter. Remember, a cubic centimeter is a unit of volume, so this is mass per volume, or grams per liter, mass per volume. So density is always mass per volume. But the way that we measure mass, kilograms or grams, might change. The way that we measure volume might change. Cubic meters, cubic centimeters, liters. As long as it's a mass measurement divided by a volume measurement, then it's always a measurement of density, even if the mass and the volume units change.